Okay, good morning, everyone. Venkat, happy 65th, 66th birthday. Okay. And I'm so pleased that I was invited to make this presentation. Process safety and artificial intelligence. Well, those of you that know me, I do know something about process safety, but I don't know a whole lot about artificial intelligence. So I'm going to do my best to try to interpret aspects of process safety and how the field relates to artificial intelligence. Okay, I'm going to stand up here. I was hoping to be able to get a little closer to the slides, but we're recording, so forgive me. Okay, so process safety. Okay, this involves rare, undesirable events. And they're predicted with little, if any, occurrence data, fortunately. Okay. They're accompanied by extensive near-miss data, which are less meaningful. Okay, so for successful artificial intelligence with machine learning, big, reliable data are needed. Okay, now before I go any further, I want to give some credit to our current doctoral researcher, Vikram Sudishan, and my very close colleague, Professor Amish Patel. And Amish did his PhD at Berkeley, and he's a molecular modeling expert. Okay, he does molecular dynamics. And in listening to one of my doctoral students present something on safety, he made some suggestions about how we could go about understanding the rare paths to accidents. So let us, with that background, I will then proceed. Okay, I hope you can see all this from the back. This is not a very big screen, but I'll do the best I can to describe it to you. What are rare safety events? Okay, well, let us take a good look now. We have normal operation. The normal operation is taking place right here in the green belt zone. We're operating with control. Okay, and every so often the controllers don't quite do it, and so what you have is a situation where you have an alarm going off, and so there's a safety system. And that safety system, I call that safety system, oops, I did not want to hit that one. Oops, hold it. Let's get back there. That safety system is such that it's usually very successful. Okay, and it usually brings the, takes that abnormal event and brings it back and brings operation back into the green belt zone. Okay, but occasionally what you have is the situation where, the safety system doesn't quite do it. So it moves on to say a high or a low alarm. And similarly, another safety system goes to work and it generally will bring it back and so on. You might do that a few times until at some point you hit the location where it's becoming very dangerous and you're going to start to initiate a shutdown and avoid an accident. And so you have a situation where you're in the red belt zone. And now the key thing to keep in mind, if you're working with AIChE, as we have been doing for quite a while, we're working with the steam methane reforming plant. And, say an abnormal event would be when the steam pressure goes down. And that happens quite often. And over a 3-year period, it happened 3 times that we got into the red belt zone, and you have only about 10 minutes or so to respond. That's the problem. 3 years, you wait, and in 10 minutes, you've got to act. Okay, so that's a big problem, and you don't have any data to speak of. So how are you going to predict, an accident of this type with so little data? Okay, well, you have a lot of near-miss data. Oops, darn it. Sorry. I have to get used to this. All right. Okay, you have a lot of near-miss data, label it as such. So Okay, our concern now is how might you use that near-miss data. Okay, so let's move on a little further. Let's just look at a given variable. You know, your normal operation would be, say, in the green belt zone, you would be trying to meet a certain set point, and your controllers are working and they're doing quite well, but every so often, you know, you have a low threshold alarm or a high threshold alarm, and okay, and if all goes well, the safety system brings it back in and so on. And occasionally, what's going to happen? Very rarely, you'll get into the red belt zone. Okay. So, moving on from that. All right, the concept of, you know, using an event tree. Okay, well, you can do that when you're working with postulated abnormal events. You're thinking in advance. You're designing your safety systems and your alarms so that they act well on something that you've postulated. Okay, you do that in the early stages of design. You look very carefully, do has-up analysis and so forth, and you try to avoid these kinds of concerns. But, of course, you know, what tends to happen is that, you know, the abnormal event comes up here, an alarm goes off, the safety system goes up into play, and it's usually very successful, that first safety system. You see what you have. You have a failure probability here. It's very, very small. Okay, and normally what happens is you just go back to continued operation in the green belt zone. Okay, well, and maybe if it didn't quite take it back, so you know, the second safety system goes to play. And that's going to have a somewhat higher failure probability. And you know, you go to the third safety system. And the third safety system, similarly, it's going to be a higher failure probability. At some point, you're going to get down to the place where you've postulated there's going to be some kind of a shutdown or an accident. And you know, so you want to predict, you know, what's the failure probability that this is going to occur? Well, you just simply multiply these failure probabilities to get that. Okay, that's dynamic risk analysis. Okay, that's what we carry out. Okay, we have programs to do that. All right, now that's what you do, say, for one particular variable with an alarm going off, but of course what's happening in plants is that you have multiple alarms going off, and the data historian is essentially giving you this kind of data on a regular basis. And so you've got the date and the time of the alarm and the alarm type. It's a high alarm or a low alarm. Oh, its priority, it could be very important, or maybe it isn't so important, and so on. And so you keep track of all that information. Okay, now, then you go, and I'll go back to Anko Periani's paper maybe 10 years ago of the data compaction. I mean, you've got to compact the data. Why do you have to compact the data? Well, because, look, in an industrial processing facility, you're going to see as many as 500 to 1,000 alarms that are going to occur daily. And over a period of, say, 3 or 4 months, I mean, you will see as many as 100,000 alarms going off. And each of those in the historian, and when all that data is sitting up over here, and, you know, it's available to you, and what Anko discussed in his paper was how you essentially identify the relevant alarms and the key variables potentially leading to rare accident, and you need to do a certain data compaction in doing that. And with the compacted data, what you're going to do is typically you'll use a Bayesian analysis to estimate the failure probabilities of the safety systems. So there's a lot of data there. But a key question is, are the data reliable? It's near-miss data. A whole company's been formed basically to make this kind of near-miss data available, and they've been quite successful in near-miss management. But is it that reliable? That's a key question. So if you're going to try to go further with this and do something in AI with all of this data, is it sufficiently reliable to find that little accident out there? Okay. All right. Let us continue. Whoops, got to do this. All right, now, many accidents they occur from unpostulated abnormal events, right? And like, for example, a hairline fracture occurs. Okay, it's unpostulated. You can't quite predict that. Sensor failure. Okay, or an earthquake, for goodness sakes. An earthquake occurs and you've got all these little fractures and so forth. You have operator distractions occur. Something went wrong at home or whatever, and the person's mind is on something else, didn't get a good night's sleep. And so those are unpostulated. Okay, so how could you proceed with that? All right, not going to make event trees for that. Okay, so you consider a fairly simple example, the CSTR. Okay, and that's what we started with a few years ago and written a couple of papers. And you have essentially A going to P, exothermic. There's our famous CSTR. Assume that it's very well mixed. Maybe you'd need a better model. You might do that. But anyway, what we have here is the stream coming in. It's got some component A in it, and it's going to react, and it's leaving here, and it's giving off energy, and we're measuring the temperature, and we're using cooling water. Okay, you all know this problem. Okay, so here we go. So you want to write the mass and energy balances, okay? And you certainly want to be controlling, of course, so you've got to have the controller on there. And, okay, so here are the balances. I don't think I need to go through these with you so much. These are just the rate at which the A comes in and A leaves, and the difference, of course, we understand. And then, of course, you have a certain amount reacts, and then the total of those two together will affect the accumulation, okay, and the change in the concentration of A. And similarly, you do the same thing for the energy balance, and with the energy balance, you'll have some heat loss. You'll have the heat of reaction to be concerned with. You'll have some heat loss to the cooling water, okay? And then you've got the cooling water balance, and so the energy balance for that. And as simple, in this case, the analysis was done with just proportional control, but that's an easy thing to make more interesting. Okay, now, what I didn't go mention as I was going through the model is this little thing called eta. And that's some noise, okay? That's the noise. And a key question when you're doing this kind of analysis is where to put the noise. You don't have much choice in this case. You don't have much choice. You've got two variables, okay? Temperature and concentration. But for other processes, it gets considerably more interesting. Okay, so, okay, it's going to represent the unpostulated abnormal events. And we're going to sample every time step, okay? Some kind of a normal distribution, okay? And it's going to have a certain variance and so on. Okay, so now the noise has come in, and I hope you can see this from back there, but most of you should be very familiar with it. Okay, there's the concentration leaving the reactor. Here is the temperature. I'm sorry, that's temperature, my mistake. This here is the conversion, okay? And so you should be familiar. As we change the residence time, Daum-Kula number, okay, what you're doing essentially is you're moving across here, okay, and the conversion and the temperature are increasing some. And then, of course, what happens is you enter a region of multiple steady states, and you come up over here at high conversion and high temperature, okay? And, of course, you can expand that so you see it a little better. All right, so, okay, what we've been doing is looking at the situation with noise and starting at different residence times, okay, and seeing what will occur, right? So first, now, of course, to get these curves, I guess I didn't mention, but it's pretty obvious, these are steady state solutions. So if you go back to the model, you simply set the derivatives, the time derivatives equal to 0 and solve essentially for temperature and conversion at the steady state. Okay, so very good. Now we're going to run a couple of experiments here. And the experiments will look something like the following. We're going to begin at a low residence time. So where are we? We're very close. We're going to be up here at high conversion, high temperature, and there's a cliff here. And we're going to jump over the cliff and quench, Okay, so that's a reliability issue. On the other hand, if we were on the other side over here and we're at the low conversion and, okay, we get too close, we're going to have ignition, all right? And that would be perhaps a safety issue. Okay, so anyway, we're looking now at the situation where we're very close to the cliff. And notice what happens is we start at, say, 800 degrees here, and it just, the noise is doing this, and suddenly, after some time, the initiation time, we get then the transfer down to the B basin, okay? Interestingly enough, this transition time is very much dependent upon where you are in the residence time, but the time that it takes to get down here, this is on a scale of about 1,000 minutes. This is just 13 minutes. It's a very short time, okay? Which is so typical of safety events, all right? And here, now we're further away from the cliff, so it's more stable, and it just takes longer to get there, okay? So that's interesting. But then there's this situation, which is so interesting, because what happens is if you get further away from the cliff and you use more noise, you increase the variance of the noise, what you're going to see now is, you come off the cliff, you go down to the basin B, okay, and look at this, it's down here and it suddenly comes back up again, and then it goes down again, and it stays up there for a while, and then it goes back. Okay, well, we can look at those rates. I mean, we've got all this data here, and when you look at the rates of the forward moving down to basin B and then going back to, KB, the ratio of those two rates, that's cap K, they don't change very much to cap K. And it turns out that the free energy of change is very similar. Okay, and it's a very important way of characterizing the data. So if you've got all of this data, would you try AI on this when you can reason like this? Big question. Okay, so now I'd like to just raise a couple of key questions and then sort of finish off on this. For such rare paths, can the committer probabilities, so what's a committer probability? It's the probability that you will reach basin B, okay? So, okay, and the rates, we can, the rates can be estimated, and we would like to correlate them with the process variables. We would like to do that. And if so, perhaps these can be used in the dynamic risk analysis to sound more reliable alarms as unpostulated abnormal events occur. Let me look at the time here now. Okay, my watch says I had 20 minutes, and so that's exactly, I have about 3 minutes to go. Okay, thank you. This would require a sufficiently rigorous process model, adequately, and very important, adequately positioned noise. And of course, model improvements could be instituted as in the vicinities of the rare paths. So that's something to keep in mind. And I'm going to skip over other concerns here because I want to do something very important before we quit. And that is, I want to return to Venkat, personally. We've interacted for about 40 years, okay? An absolute pleasure. In these different places we've done. We've benefited from your ability, okay, to suggest and implement promising and innovative solutions in the most diplomatic and favorable light, often surprising us when they were successful. Okay, so that's an observation, okay? Here we are. We're in Rodosh, and there's my student, George Prokopakis, and if you knew George, every week he had another great idea, okay? So, I had my list of great ideas that he had, and come in the next week, and I just, what happened on that one? No. So when he graduated, we had a party, and I gave him a list of ideas that needed to be finished. And I said, one of them is organize a sailing trip in the Greek islands. Okay, so we're in Rhodos, and we're attending the Escape Conference. And, okay, there's George. And guess what? Okay, Venkat is with us on that trip. Had a very good picture, I think, that came out. And who was behind him? Right over here, Rex, okay. And so that was our trip from Rhodos to Simi along the Turkish coast, okay. And we finally got to Simi, and there are some of the people, Venkat over here, okay, and George is over here, and this is another George, Rex's son, and Rex and Diane and myself and Vasilius Vasiliadis. Okay, it was a great time together, and I wanted to remember that, and I just want to say, Venkat, happy birthday, many healthy ones, healthy birthdays with successful years enriching the lives of your family, colleagues, students, and everyone. My pleasure. Thank you.